Hello. This will be the last recording related to chapter 7. We have to finish a couple of theory concepts and then we'll proceed and look at some problems. So, this slide, slide number, I don't know what it is, it's a slide, let's see. 65, 64, 63. Okay, so this is slide 63. The slide numbers have gone behind the images. All right, on this slide, I will explain what this complicated looking circuit is all about. And this is figure 7.31 in our textbook, and it's called the generation of a number of constant currents of various magnitudes, right? Different magnitudes. So we didn't do too much of this in the MOS. We just said it's possible depending on the ratios of the aspect ratios. Yeah, W by L divided by W by L. Here we'll do some actual examples for the BJT case. So first of all, the way the current mirror that is used to generate the source current I0 itself is slightly different, right? So if you look at the previous slides, here the resistor is connected to VCC and in the collector circuit of Q1, and then the bases are just directly tied together and the emitters are grounded, right? That's how this was created. Here he's showing it slightly differently. The emitters also, we are taking an PNP and an NPN and together creating a reference current, okay? So it's kind of a different approach. I don't know why he did that in the textbook, maybe to confuse us even more. But anyway, I'll walk you through exactly what's going on. So first of all, I reference, right, is generated by this combination of Q1, Q2, and R, right? So that's step one. Once you have I reference, then you create the first of your output currents, and then if you have the patience, you can create many more output currents, right? So next step is Q1 forms a current mirror with Q3, right? Q1 and Q3 are connected as a regular current mirror, as we have already seen. So that will create a constant current I1, right? So the reference current again is slightly different from what was shown previously, but Q1 and Q3 forming a mirror and creating I1 as an output current, that follows the same logic, right? We've seen that before. The only thing is the emitters, this is a PNP, while what we have seen so far was an NPN, right? Okay, so Q1 forms a current mirror with Q3. Q3 will supply a constant current I1 equal to I reference because Q1 and Q3 are matched. Q5 and Q6 are each matched to Q1, right? Now look at Q5, Q6. They're also matched to Q1. So same EBJ area. But what you'll notice is they are totally connected in parallel. The two emitters are connected and the two collectors are connected together. And of course the drains are. So given that they're all connected together, that makes the two transistors totally a parallel connection, okay? So just remember that. So hence what happens is this combination behaves as if the emitter base junction is twice the size of Q1, right? If you take the two emitter base junction areas together and add them, then that becomes twice. So it's almost like the ratio of the emitter base junctions is 2 to 1. Hence this I3 becomes twice the I reference or twice of I1. Okay, so that's an important point to remember. Similarly, Q2 forms a mirror with Q4, right? So you have Q2 here, and here these are all NMOS devices. So this forms a mirror with Q4. It creates its own output current I2. So it provides a constant current I2 also equals to Iref. Now Q7, Q8, Q9 are each matched to Q2, right? They're also connected together and there's three of them. So you can expect that this current I4 is thrice the I reference or I2, right? So that is another formula that I've shown here. So some of these I've written myself, they're not in the original drawing, but I hope this clarifies it. Lastly, we talk about the importance of the saturation condition keeping them in the active region condition, right? Because these are BJTs. So Q3 sources its current. So Q3, right? Q3 is pushing current I1 into a load. So it sources its current to parts of the circuit whose voltage should not exceed VCC minus 0.3. So the voltage at this point, VC3, collector 3, should be less than VCC minus 0.3 volts. Similarly, Q4, which is here, it sinks current, it's drawing current from parts of the circuit whose voltage should not decrease below. That means the voltage at this point, VC4, I should move that up here, sorry, because this is the emitter, that's the collector. So this VC4 has to be there, has to be greater than minus VEE plus 0.3, okay? So those are the saturation conditions. So it's a slightly complicated circuit compared to what we have seen thus far, but this is what's been used a lot in examples and problems. So we'll do a few more problems on BJTs. And with that, we should be done with the theory. Well, actually, I have one last section, 7.5, which I've not mentioned so far, but maybe quickly we can look through this, although in the next few minutes, because it is in the syllabus to cover. I'm not going to do any problems and don't expect any exam problems on this, but this is good general information. So we have seen the current mirror circuits, the current steering business. Apparently you can improve these slightly, right? And there's 5 ways that you can improve this method slightly. Improved performance meaning what? More accuracy of the current transfer ratio of the mirror, right? So we know for BJTs, for example, because of the variation of beta, and even for MOS devices, we are dependent on, the threshold voltage VTs, which sometimes can vary. So better accuracy of the current transfer ratio or the current gain is something we are always concerned about, and also higher output resistance of the current source RO. So you have a current source that gives you a current of IO, but it also needs to be at a high output resistance generally. So how to increase the output resistance RO? So these 5 methods apparently are proven to be better to or improve the performance of our mirrors. The first one you see is cascoding, right? So we have learned the idea of cascoding a transistor by adding another transistor, similar transistor, in a common gate or common base format configuration, and that improves the output resistance. So here you see that by this connection and having 2 more transistors, Q3 and Q4, the output resistance can be raised from just being RO2 to GM3 RO3. Okay. There's a disadvantage, more transistors meaning more power supply being consumed. Here's in the bipolar case, there is a way of connecting a third transistor to reduce the variation of the beta, right? So previously you had 1 plus 2 by beta. Now that beta has been replaced with a beta square, and so what he says is the error due to finite beta has been reduced from 2 by beta in the simple mirror to 2 by beta square, which is a great improvement. Okay. Then we have one more connection called the Wilson current mirror. Instead of having the third transistor connected like this, here you can connect it like this, and you achieve the same benefit, and apparently the other benefit is the output resistance also increases. Okay. There's another variation of the Wilson mirror. So this is also a Wilson mirror for BJTs. This is a Wilson mirror for MOS. Same idea. bring one more transistor or bring two more, then it looks almost like the cascode version. But nevertheless, in each case, you are improving the output resistance by this factor. You're raising it. The last item is what's called a current source, the Widlar current source. Here, the big advantage is that a resistor is included in the emitter circuit of Q2. Remember, we said no resistors, right, inside the circuit. But the advantage is that small resistors, when introduced, can help improve or you're able to implement a current source using small resistors. So using the Widlar circuit allows the generation of a small constant current using relatively small resistors. Another important characteristic of the Widlar current source is that its output resistance is high. So there's an example 7.6 in the textbook that we won't look at, but it proves to you that if you have two circuits, one a normal and one with that emitter resistance, instead of having one very high resistance to create your I reference, apparently you can take two smaller resistances, much smaller. If this is like a mega ohms, this is like small kilo ohms, to get the same benefit. Okay. All right. So with that, I will stop or pause the theory portion, and we'll come back and look at the problems for the next 20, 33 minutes or so. Okay. 20, yeah. Okay, so we actually have 32 minutes to do some problems. So let's start by looking at an example from the textbook, and this is example 7.5. So again, I'll let you look through it in detail, but it's an important first example. You should become completely familiar with it, because a lot of the other problems and questions that we will do in the future will all revolve around many of these concepts, and you should become comfortable working with these numbers, these formulas, these quantities given here. Okay. All right. So just to see what the problem is all about. So VDD is given. I reference has to be 100 microamps. That's the goal, right? So if I reference is 100 microamps, we also want an output current which is also 100 microamps, right? So it equals the I reference. If that is the situation, then a few things we require. Find R, which is here, and a bunch of other conditions are given. What is the lowest possible value of VO, V output, that we can work with before, because remember the MOS has to be in saturation, so it can't fall below a certain minimum value. So what is that? Then find the output resistance RO in this case, and also what happens if there's a plus 1 volt change in V output. Okay, so straightforward application of a variety of formulas that we have studied so far. I don't see anything that is very difficult, so I will leave you to look through that. For example, very first thing, R we need to find, right? I told you R can easily be found as the voltage divided by the current, Ohm's law. What voltage is being applied across R? It's VDD minus this VGS. To find VGS, the formula is you add VOV and VT, right? We don't know VOV, which is found by that other formula for current, drain current, in terms of all the other parameters like W by L and all that. So he shows you how to walk through that, and please follow along and make sure you understand the example. All right, I'm going to move on. We've got a problem from the back of the chapter 7.47. Same situation, we have a current mirror to cause a current source. So we have a given VDD, a pair of matched MOSFETs, design the current source circuit to produce an output current of 150 microamps. Previously we saw 100 microamps, now we want 150. So what should the value of R be? All the other stuff is given, Vt is given, there's an early voltage given. To simplify matters, assume that the nominal value of the output current is obtained at VO equals VGS. It is further required that the circuit operates for V output in the range of 0.3 to VDD and that the change in I/O over this range be limited to 10% of the nominal value of I/O. Find the required value of R and the device dimensions. That means Wi by Ls and so on, because that is not given. A lot of other information is given, but the W by L and Ls are not given. Alright, so here are the formulas. The output resistance is the first thing to be calculated using this. I/O is given, VAL is given. Then we always have to rely on this formula. In this case, I think we use this formula. This we have seen before. I may not have given you this, so I thought I'd bring in this also. This lambda is nothing but 1 by VA. So this formula can be changed to read like this. And then these other formulas I'm sure you know, and you know the formula for R, right? So all these are known, or something you should be comfortable with. So VDD, I0, which should be I reference, these parameters are given. Change in I0 is 10% of 150 microamps, or delta I0 is 15. So V0 also goes from 0.3 to 1.8. So delta V0 is 1.5. So R0 is defined as delta V by delta I. So that comes out to be 100K. Another form for R0 is VA by I0, VA prime L by I0. So 100K is this, from which L comes out. Remember, this L, when it comes out, is directly in micrometers. I've said that before also. Since VA is VA prime into L, so VA is 15 volts. Now we need to find W by L and R to finish the problem. Use the formulas this and this. So VOV is given, DS min, which is 0.3 volts. VGS is VOV plus VT, that's 0.8, and you need to substitute V, well, let's see. So ID equals I reference, right? And this VGS is what we are going to use in place of VDS, because that's what he says to use, right? We output, use it as equal to VGS, and output is nothing but drain VDS, right? So in this formula, instead of VDS, we can use VGS. So this formula, 150 on the left side, microamps, everything else except W by L is known, from where you can then say W by L is 7.91. L is known, we just calculated it, so W becomes this. R then becomes VDD minus VGS by I reference, which is 6.7 kilo ohms. Okay, so that's how we solve to find a bunch of unknowns on 7.47. Moving on, there's an exercise problem related to MOS steering circuits. I thought the exercise you know is in the chapter, and the answers are also available. I thought this was a good example to help us understand this circuit, which we have seen in the theory also, right? All this stuff. So it's a straight application of all these formulas that we studied when we were studying this. Okay, so a bunch of things are given. VDD is given, VSS is given, VTN, VTP, channel lengths are given as 1, Kn prime, Kp prime, these are V squares by the way, and there is no lambda to worry about, so we can use the simpler formulas. Like for example here, the formula is simpler. So the I reference has to be 10 micro. Find the widths of all the transistors to obtain. Now it gets interesting, right? I2, we don't just want it to be I reference. We want it to be 6 times I reference. Similarly, I3, which is also I4, we want it to be 2 times. See how they are nice integer multiples of this I reference? Finally, I5 is 80 micro, which is 8 times I reference. So what that means is your W by L ratios is what you have to tweak or adjust, right? The ratios of the W by L ratios is what you have to tweak, okay? Alright, it's further required that at the voltage at the drain should be allowed to go down to within 0.2 volts of the negative supply. That means at the drain of Q2, which is this, the drain of Q2, the voltage should be within 0.2 volts of the negative. So the negative is minus 1.5, so it should go up to 1.3, minus 1.3, and that the voltage at the drain of Q5, which is this drain, should be allowed to be within 0.2 of the positive. So if it is 1.5, we're allowed to go up to 1.3 on the drain of Q5. So that's another condition. Okay, so we have these formulas that tell us how to handle this set of conditions, right? These are the saturation conditions. We saw these already, so they shouldn't come as a surprise. Similarly, the relationships between I reference and any of these other currents is through these W by L ratios, right? So we've seen these before, so we're going to use them. Lastly, to find the WILs, you use this formula because I2 is given, I5 is given, so the left side is given, many other things are given, and then W by Ls we can quickly find. Once we have that, we can plug those in to get other W by Ls and the W's more importantly. Okay. Lengths are constant at 1, that makes it easy because in all these formulas L just becomes 1. Alright, so I will look at 716 next. So I reference is 10, I2 is given to be, must be 60, I4 equals I3 should be 20, I5 equals 80, VDD is VSS is 1.5, VTN, VTP are given, L is 1, and all this other stuff is given, and all these L's are given to be 1. Great. So I2 should become this ratio or this formula, and I reference is 10, so L is 1, so if you just take L out of consideration, you get these simple relationships. W2 by W1 is 6. Similarly, W3 by W1 is 2, because I3 has to be 2 times, right? 20, right? So 20 by 10, 60 by 10, 80 by 10, 20. Because remember, between I5 and I4, it's not 10 in the denominator, because I4 is already 20, so 80 by 20 equals 4. So these ratios W2 by W1, W3 by W1, W5 by W4 become convenient later on. Now to find W by L2, use this current formula. To find W by L5, use another current formula. Okay. To allow the drain of Q2 to go down to within 0.2 volts of minus 1.5, that is, it has to stay above 1.3, minus 1.3, right? So minus 1.3 is minus 1.5 plus V over 2. I think this is this formula where we just use the equal to instead of the greater than. Oops, I don't know why I did that, yeah. So OV2 is 0.2 volts. Similarly, the other condition to allow the drain of Q5 to go up to within 0.2 volts of 1.5, that is to stay below 1.3 volts. So this, and so OV5 also comes out to be 0.2. So both overdrive voltages are 0.2. So using that 0.2 in this current formula, you come up with W by L. L is 1, so W2 you know. Similarly, W5 you find out using this current formula. Then we use those relationships previously found to find W1, W3, W4. So we found all the W's and we found all the R's, or the one R. Okay? All right. Sorry. What was the value of R? R is, oh, we didn't need to find R. Oh yeah, we didn't need to find R at all, just the W's. And here's the answer given in the textbook anyway. Yeah. Okay, anyway, that was that problem. Then we have another problem on MOS 751, also from the back. So here, like I said, the circuit is slightly different, right? The PMOS stuff is on the top, the NMOS is at the bottom. The current reference is generated by the PMOS. Same idea though, the resistor is in the drain circuit, and you get I2 as one of the currents. I3 is being used as a reference for this mirror, I4, I5, and then you get one more current, I5, right? So same thing is just flipped around with the PNP and PNs, okay? So design the circuit so that I reference is 20, I2 is 100, I3 equals I4 is 40, I5 is 80. All devices have the equal length, 0.5. Use the minimum possible device width needed to achieve proper operation of the current circuit Q2 for voltages at its drain, Q2 at drain as high as 0.8 and sink Q5 as low as 0.8. So previously here he had given the wording they used was to within 0.2 volts, right, of the supply voltage. Here luckily he just says 0.8 minus 0.8, which is the same thing. It is 0.2 volts of the 1 volt supply voltage. Specify the widths of all the devices and the values of R. Find the output resistance of the current source 2 and the output resistance of the current sink 5. So pretty much similar problem. I don't know that really there's too much else, except that we start with using PMOS to find the overvoltage value, 0.2 volts, which we found previously. Also OV2 equals OV3 is both 0.2. Similarly NMOS, you get the overvoltage as 0.2. So given that the reference current is equals ID1 is 20, then you can come up with W by L 1 from this formula. Also L1 is given, so W1 comes out immediately. Since Q's current mirror Q2 or Q1's current mirror Q2 has drain current of I2 equals 100 microamps, then the ratios of the aspect ratios is 5, 100 by 20. So W by L2 is 50, L2 is known, so W2 is 25 micro. Similarly, Q3 is also a current mirror, so I don't really see that I need to do too much more here. We found all the W's. I put the arrows to show you the W's, W3, W4, W5. To find R, yeah, the PMOS formula is slightly different. You write, instead of GS, you write SG, right? Then you find R as 15K. Output resistance of the transistor 2, output resistance of transistor 5. Okay, so almost same as previous example, but I wanted to do both examples because I can tell you from an exam point of view, you can expect a problem like this to appear. This is the heart of your whole MOS current mirror, current steering logic, and it's so important because you'll use it in all of your electronics courses in the future also, right? All right, so I'm going to move on to BJT circuits. We have another 15 minutes. I don't have too many, but I do have a couple. All right. So 7.57. Okay. So here, sorry, of the figure. So Q1 and Q2 are matched and I reference is 1 milliamps. The early voltage is also given as 90 volts. Neglecting the effect of finite beta, so that means ignore the finite beta. Find the change in I/O both as an absolute value and as a percentage corresponding to VO changing from 1 volt to 10 volts. So that's the problem. So it's a pretty simple problem. I think it's a straightforward application of the formulas. So it's an introductory problem to BJTs. Let's think of it that way. So I0 equals I reference is 1 milliamp and we are told that VO changes from 1 volt to 10 volts. So RO2 is delta N VO by delta N IO, which is 10 minus 1 by delta IO, which is 9 by delta IO. Similarly, another formula for RO2 is VA by I, which is 90. So this 90 equals this, from which you get the change in current to be 0.1 milliamp. So the percentage change is from 0.1 to 1 or 10% change. So as VO changes from 1 to 10 volts, which is a 10 times multiplication, right? It's a pretty big change. IO only undergoes a 10% change, 0.1 to 1 milliamps. Okay, which is also a 10 times change, but in milliamps. All right, so that was a first problem on BJTs. Then we come to, the steering circuit problem. And then I don't have anything on this section. So let's just finish off the two current steering problems I have. To see that. Okay. So let's look at these two current steering problems. This looks like it's a complex circuit, no doubt, right? And even these nodes, I stuck them in there, but in the original problem, you were just given the circuit and you were asked to find the voltages at all the nodes and the currents through all the branches in the circuit. Assume VB is 0.7 and beta is infinity, right? Also assume all transistors are matched. So essentially you need to find currents and voltages everywhere. So when we say everywhere, like the voltage here, the voltage here, here, the voltage 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 here, and so on. Okay. So let's start with something very simple, which is what is the voltage here, right? Now we know VBE is 0.7. So if you go down this path, this 5 volt drops base to emitter 0.7 as given. So you are left with 4.3, 5 minus 0.7. Similarly here you have minus 5. So if you go up here and you drop 0.7 here, you are with minus 4.3. So the first current R1, the first current I reference flowing through R1, and this Q1 Q2 forms your current source. Q1 R1 Q2 forms your current source. So first let's find that I reference current, and we know the formula is this formula, right? So you take the VCC, take out one BE voltage, you take the VEE, you take out another BE voltage, divide the whole thing by R, which is basically what I've done here, right? Because we've already taken this and dropped it to 4.3, we've taken this and dropped it to 4.3, minus 4.3. So the current here is the voltage here minus the voltage here by R, which comes out to be 0.43. So we found one current here. Now let's look at the other stuff in this complicated looking drawing, right? So now the thing to remember is, first step we found I. All 11 transistors have the same 0.43 current in their collectors. They're all matched. There is no paralleling of circuits, right? That compared to some of the previous example, where here we saw some paralleling, but that paralleling, we'll look at it in a second. Sorry. Yeah, but otherwise, in the drain circuits, in the drain arm of each one of these transistors, the current is the same, and that's 0.43 milliamps, okay? Because they are all generated from the same reference and the transistors are all matched. So you can go ahead and blindly put 0.43 in every branch. Once you do that, then it becomes easy. Now, I've also shown you what transistors form what mirrors. So for example, Q2, Q7, Q8, Q9 is a mirror, right? Q2, Q7, Q8, Q9 is a mirror. Q1, 3, 4 is a mirror. 7 and 8 is a parallel combination. Where's 7 and 8? Yeah, this 7 and 8, because they are tied on both ends and the basis is tied, they form a parallel. And you know, when it's a parallel, then the total output current is the sum of the two, right? It's the product of the two times. So that's one parallel combination. So those are some things I noticed. Now, the voltage across the resistors. R1, where R1? This is R1. So that's just 8.6, 0.43 times 20. Or you can just say it's 4.3 minus of minus 4.3, right? We use that here to calculate this top portion. So whatever is that voltage, this is 8.6. R2 is here. There's only 0.43 flowing in 8K, so you multiply the two. R3 is here, 0.43 times 3.6. R4, here, because of the parallel combination, this current is twice the individual currents, so it's 8.86 times 5, and with a negative sign, right? Make sure you understand that, because we are showing the current to be flowing like this. So it's flowing from negative to positive is how we show it. Hence the voltage drop we say is with a negative sign. Make sure you follow that logic. R5, which is here finally, is 0.43 times 10K, which is 4.3. Okay, so it's a little bit crazy looking circuit, but once you identify the fact that Q1 and Q2 form the source mirror, and you can, given R1, it's easy enough to find I given the two voltages on either end, plus VCC and minus VEE. Once you start with I and you apply I to all the other transistors, and then follow this one rule for this parallel combination, I think pretty much it becomes a simple exercise. So a complicated looking circuit, but I think the answer isn't all that complicated. Now this was only possible because we are ignoring beta, right? That way we are just taking the current, one current value 0.43 and applying it everywhere. If beta was finite and given in some value, then we have to start applying that for every pair, that more complicated formula, right? Yeah, this formula with the beta, and boy, every current would have been coming out to be different, right? So luckily we don't have to worry about that. Okay, all right, one last problem and we should be done with chapter 5. Chapter 7. I guess I'm going crazy. Here also we have a current steering circuit using BJTs. Not very clear again where we should be looking for the current mirror, but this I reference I put here, and I recognize that Q1, Q2, just because it's Q1, Q2 and there is an R, you can think this is the current source that gives us our first current, which then becomes translated everywhere. Now another confusing thing is he wants us to find I, but we can see that I is the output from a parallel combination of two transistors, right? So automatically this I is twice of the currents in the drain, in the collectors, which is I reference, right? So he's kind of played a trick on us. Instead of calling all these I, he's called this I. So all the other currents, the actual reference and source currents, are all I by 2s that we need to find. Okay. All right. So again, the only data given is that luckily beta is infinity, VBE is 7.7. So find I, V1, V2, V3, V4 and V5, which is V1, V2, V3, V4, V5 for two different situations. Given R is 10K and given R is 100K. Okay. So how do you solve this problem? This is the next one. Beta equals infinity means currents in all the base circuits can be neglected and the simpler formula can be used. In Q1, right, V1 equals EB1, right? So this is Q1, and because the base is grounded and we know EB1 is minus 0.7, so this V1 is automatically minus 0.7, right? Because EB1 is given. So current in R, say the I reference, is this voltage. The voltage across, remember this emitter after the resistor is connected to minus 2.7. So the current here is this voltage minus this voltage divided by R, right? So that's what I do here. Minus 7 minus a minus 2.7 divided by R gives you 2 by R. If R is 10K, this reference current becomes 0.2. If R is 100K, this reference current becomes 0.02. In either case, one thing to remember is that the product of I and R is 4 volts, which is because you take this I and you multiply by, this is I reference, right? And we said that I reference is 2 times or half of I, or I equals 2 times I reference. So that's 0.4 milliamps. So IR, whether it's 0.4 or 0.04, always comes out to be 4 volts, and we use this somewhere below. So that's a small trick to remember. Anyway, so we found the two currents for two different cases of R. I reference flows in Q3 and Q4 also, right? So this I reference flows in Q3 and Q4, and they add up together to form I5. We can see that I is twice of I reference, so that's, and we want this I, so these are the values of I. V2, V3, also note that I splits equally between Q5 and Q6, so V4 comes out to be this and V5 comes out to be this. Here for IR I use this 4, here also for IR I use this 4. If you do that, you can find V2, V3, V4, V5. This V3 is connected strangely. Yeah, V3 is again just the base voltage, right? Because the base is grounded, whatever we are given as BE is also V3 from both sides, right? So that gives us B3, okay? So with that, we found everything that is required. So take a look, make sure you understand the logic, and with this, we complete chapter 7, and that's quite a great achievement. So congratulations. Next week, we'll come back and move on to the next chapter, chapter 8. Thank you.